In the last series of videos, we talked about section 11.2 on series, and we saw the divergence test, or nth term test, which was the first of our tests to tell whether a series converged or diverged. In this series of videos, we'll talk about the integral test, the second of our tests to tell whether a series converges or diverges. And the big idea is to compare a series to an integral. I'll start by telling you what the integral test says, and then we'll do some examples. The integral test says, suppose we have a function f that has three properties. It's non-increasing. That means it doesn't have to be always decreasing, but it can never go up. So it's non-increasing, it's continuous, and it's positive, real-valued function on the interval from 1 to infinity. So it doesn't matter if it's not continuous at 0. It doesn't matter what happens when values are negative. Between 1 and infinity, it has to be non-increasing, continuous, and positive. Then we're going to use this function to make a sequence. F of capital N will be equal to an. What the integral test says is if this integral from 1 to infinity of f of x dx converges, if it's less than infinity, I'm using this as a shorthand for converges, this integral exists, the limit that defines this integral exists and is some finite number that's not plus infinity, then this series S, which is the sum of n from 1 to infinity of an, also converges. So if the integral converges, the series converges. Well, what if the integral goes off to infinity? If the integral from 1 to infinity of f of x dx is infinity, if the limit that defines this integral is infinity, then this series also goes off to infinity. If the integral converges, the series converges. If the integral diverges, the series diverges. So how are we going to use this test? Usually, you're given a series to start with, and you build your function from that series. So we've already seen how to do this in some examples where we wanted to compute limits involving L'Hopital's rule. And then you'll have to compute an improper integral from this function, and that'll tell you whether or not the series converges. So I'll pause and erase, and then we'll do two examples. Let's start by looking at the series given by a sum from n equals 1 to infinity of 1 over n squared plus 1. We want to apply the integral test. So we'll take this series and we'll define a function, f of x, which is 1 over x squared plus 1. Why do we do it this way? Because f of capital N is now this an, 1 over n squared plus 1. We have to check that on the interval from 1 to infinity, f is non-increasing. Well, this is true because as x gets bigger, the denominator gets bigger. So this function is decreasing. This is continuous. There are no problems with the denominator vanishing or anything. And it's positive because it's a positive number 1 over a denominator that's positive. So we can apply the integral test. So let's think about the integral from 1 to infinity of 1 over, or let me say it this way, of f of x dx. What does this mean? Well, it's defined with a limit as t goes to infinity, the integral from 1 to t of 1 over x squared plus 1 dx. This is a function where we know an antiderivative. So this is the limit as t goes to infinity of arctan of x, applying ftc2 at 1 and t. So it's a limit as t goes to infinity of arctan of t minus arctan of 1. We've already seen in an earlier video that the limit as t goes to infinity of arctan of t is pi over 2. That the values of theta that are giving larger and larger and larger values of arctan are thetas that are approaching pi over 2 from below, so that sine is close to 1 and cosine is positive, but getting closer and closer to 0. So this is pi over 2 minus arctan of 1, which is pi over 4, which is pi over 4. Okay, so what does this mean? So this means that the integral from 1 to infinity of f of x dx converges to some number less than infinity. So by the integral test, that means this series converges as well. The series converges. It gives you something less than infinity. So let me just write a warning here. So this is something that people always find confusing at first. The integral test says that S converges. This improper integral converges to pi over 4. The integral test does not say that the series also converges to pi over 4. It doesn't. It converges to some other finite number. So let me write that down because it's important. So the integral test does not say that S converges to pi over 4. So when we talked about geometric series and telescoping series, we said that these are some special cases where we can compute the exact value of a series. The integral test will tell you whether or not a series converges by looking at an improper integral of a function built out of that series. But it will not tell you what that series converges to. It'll only tell you whether it converges or diverges. So I'll pause and erase, and we'll do our next example, which will be the final one of this video. For our next example, let's look at this series, which is a sum from n equals 2 to infinity of 1 over n times the natural log of n. So immediately there's something different, which is when we stated the integral test, we had a series that started at 1. But this series starts at 2, not at 1. Why does it start at 2? Well, if you put in 1, you get 1 over 1 times natural log of 1, which is 1 over 1 times 0, which is 1 over 0, which is not defined. So the series starts at 2. So in the integral test, the integral should start at 2 as well. So there's a version of the integral test where your series starts at any number. It could start at 10, it could start at 1,000, and you're just comparing the sum from n equals somewhere to infinity to the integral from that same somewhere to infinity. But in reality, in practice in this class, the only examples we'll see start at like n equals 1 or n equals 2. Okay, so that's a first thing that I wanted to point out. So let's try to apply the integral test. So we want to let f of x equal 1 over x times the natural log of x. Because now f of n equals an. This function is non-increasing from 2 to infinity. As x gets bigger, the denominator gets bigger. It's continuous. For 2 to infinity, we don't have any problems with the denominator being 0, and it's clearly positive. So we can apply the integral test. So let's consider the integral from 2 to infinity of f of x dx. If this integral converges, this series converges. If this integral diverges, this series diverges. Okay, so we can determine whether or not these series converge as long as we can compute some integral. So 1 over x natural log of x dx. And this is an integral that works super well with u substitution. We let u equal log of x, and then du equals 1 over x dx. We have to adjust the endpoints. So what we get is a limit as t goes to infinity of the integral. Well, we have 1 over u du. What is u equal to when x equals 2? Natural log of 2. what is u equal to when x equals t? Natural log of t. I know an antiderivative of 1 over u. So we get natural log of absolute value of u, but these numbers are positive, so it's okay to not worry about that. Natural log of 2, natural log of t. So we get a limit as t goes to infinity of natural log of t minus natural log of 2. And as t goes to infinity, natural log of t also goes to infinity. So we're getting something going to infinity minus some number. So this diverges. So by the integral test, the series diverges also. So that's what the integral test is good for. We're able to take some series that we're trying to understand and instead just work with an integral, an improper integral that you have to define in terms of a limit, but still, in this class up to this point, the main thing we've been doing is computing integrals. So we're able to replace this new complicated series object with an integral that we know and love. And in this case, it tells us that our series diverges. In the previous case, it told us that our series converged, but not the value that it converged to.